Okay, good. Thank you very much. So, Professor Saad, can you please share your presentation so that we check if there is any issue?
1 second. Yeah. Does it show now?
Yes, perfect. Okay,
Great.
good. So I think we are good to go. So thank you again for being here and accepting our invitation. And we look forward hearing now the nice seminar, okay, with this title, which is Wireless Extended Reality over 6G networks, okay, a tale of two RSs. So there was Terahertz before on the title, right? But
Yeah.
I understand. Yeah. I understand.
I got it by mistake, I guess.
No, it's okay. It's okay. Feel free. So I understand that we will hear about Terahertz now.
Yeah.
So I send the abstract to the mailing list, and we have 126 people who registered for the seminar. So let me say some words about the biography of Professor Saad. Professor Saad, he is an IEEE fellow. He received his PhD from the University of Oslo in 2010, and currently he is a professor at the Department of Electrical and Computer Engineering at Virginia Tech, leading the news laboratory. He is very well known in the area with major contributions in the area of wireless networks, machine learning, game theory, security, UAVs, cybersecurity. So really very strong contributions. Okay, he is IEEE distinguished lecturer. Okay, received for so many awards and Best Paper Awards. And he is currently serving as editor for the IEEE transaction on mobile computing, IEEE transaction on cognitive communication and networking, and editor at large for the IEEE transaction on communication. So with that said, so we give you the mic, and by the end I will be collecting the questions, and then we can you can answer them as per your time. So once again, thank you very much, and the floor is yours, Professor Saad.
Yeah. Thank you, Nizar, for the invitation. It's my great pleasure to give this talk. So today I'm going to talk about the deployment of extended reality over 6G, particularly terahertz networks. And we're going to talk about a tale of two R's that appears when you start looking at extended reality and wireless, future wireless networks. So let's start a little bit with a quick glance on the different VR, AR, different terminology. And I think probably the audience is already familiar with this, but just a quick recap. So as you know, there's in the computer vision literature, there is a virtuality, a reality continuum. And in this continuum, you can move from a very purely virtual world, which is what we call virtual reality. And my example application will be VR, although it kind of extends to others as well. And then you can go towards AR, which is the other end of the spectrum, where you have the real world, but with some supplements, augmented pieces of virtual world embedded on that. And mixed reality is somewhere in between. So a combination of virtual and real experiences like holographs, for example. And within this entire reality virtuality continuum or spectrum, we usually use the term, and that's kind of becoming more common now. We use the term extended reality to basically explain or to basically mean everything alongside this this spectrum. So extended reality is perhaps one of the most exciting applications for 5G already and for future 6G and beyond. The reason is that traditionally extended reality applications, including VR and AR, were done through wired connectivity. And that's interesting, but it limits the space within which you can use those applications. So the moment you kind of decide to go wireless and cut that cord, then you would have a much broader and richer virtual world with which you can interact. And I kind of think that in the next maybe a decade or so, we're going to have a more merger between the virtual and the physical and the human worlds in some sense. And that is primarily owing to the deployment of wireless access for extended reality applications for XR. So XR over wireless, I mean, could have many applications. So this figure shows kind of a little bit of a broad overview. So you can think of small, let's say, localized indoor applications, like, you know, you have here someone on in his backyard or in his room, just playing a small game and interacting with the virtual world within a confined environment. Or you can think of more like remote applications where there's a user here who's going through the entire wireless infrastructure to actually watch a video game or to watch, sorry, a sports game or to get immersed in a concert or visit a VR theme park. And this is kind of more like a remote application because you're sending the user all the way back to a very remote location. On the other hand, the other one could be just an edge, a confined space. Or you can have also kind of a mixture, as we said before, like holographic meetings and things of that sort. And as you can see from this figure, all the wireless infrastructure will play a role in extended reality, ranging from the use of wireless LANs, Wi-Fi, cellular, which is the main focus of my talk, and of course the different split computing architectures between cloud and edge. And they will all come into play, including multiple radio access technologies, millimeter wave and sub-6 gigahertz and beyond. So the first question you would ask, I mean, why do I have terahertz and 6G in the title? Is it just because trying to sell, or is it just a matter of being fancy? But the answer is not really. The idea is, can really 5G support, let's say, AR and fully immersive VR and XR in general? The idea is, of course, 5G is already good and it can support VR. But the answer is really, it depends what VR you want. So if we think about early days of virtual reality, these small experiences we used to have in some parks and so on, those are very low rate, but they're interesting, but they're very low rate with kind of a reasonable delay. This is something you can say pre-VR all the way to entry-level VR, and those can be supported in actually LTE. You don't even need 5G. Now, going a little bit further towards advanced VR applications, where you need like target uplink and downlink of more than 50 megabit per second, or even all the way up to 1 gigabit per second for the downlink, these can be supported with 5G now, and you have already applications that are starting to appear. However, if you go towards what some of the industry likes to call ultimate VR, which is the case where you start having fully immersive experiences or a complete embedding of augmented reality around you in a mobile environment, where you need kind of very high rates, and you need to basically send all the multi-sensory inputs through your XR system. And this ultimate XR or ultimate VR, if you're just looking at VR, is where this perceptual and haptic requirements start to kind of merge with the actual senses of the user. And in that case, you need, I mean, rates and compressed bit rates of upwards of 2,000 gigabit per second if it's uncompressed, and that's very hard to achieve. And this is a small nudge towards, you know, saying we need 6G, we need beyond millimeter wave. And I'm gonna essentially looking at the different XR, AR flavors, the different flavors of XR and how they kind of rank in terms of requirements. So looking at VR, in VR you need simultaneous visual component, which is essentially the virtual world, and haptic component, which is the transmission of your senses and of your basically gestures inside the virtual world. So in this situation, you would need extremely low latency and very high reliability. I mean, yeah, we talk about 5 nines, but keep in mind, and I'm gonna kind of revisit that point. When we talk about 5 nines and 5G, it's mostly targeted at IoT application uplink short packets. Here we're very different, and that's something I'm gonna try to highlight later on. So in this VR, and if you go towards really ultimate VR, you have applications going up to 100 gigabit per second, and a few milliseconds and even less sub-millisecond latency for haptics. And this is clearly starting to strain the 5G network. And again, this is not discounting what 5G can do for XR, which is a lot, but we want to do even more. And of course, in AR, the situation is similar, but a little bit different. In AR, the haptic component is not as important, but you need freshness of information. And I'm gonna briefly touch upon that in our kind of like ongoing works and show why that is important and how that also measures in future networks. Now, AR will share the similar rate latency reliability requirements of VR, but it's less stringent on haptics because you're not immersed in the environment. Now, when you talk about mixed reality and let's say beyond XR, where you start talking about 5 senses or a multi-sensory experience, you need to satisfy terabit per second rates. You need high reliability, extremely low latency, and of course, a stable connection, a stable low latency, not just a low latency. And in that case, you need to synchronize feedback from all 5 senses of your users. And that's really very, very challenging. For example, tactile feedback on holographs may need sub-millisecond latency. So clearly, this does not work in 5G, and this kind of motivates going towards 6G system or future systems where multisensory XR applications are a driving force. And we start looking at the different trends that can allow this to happen. There's a lot of things that you can think of, starting from smart environments to the need for data analytics, and that could have been a talk for today, but we can defer it to a future talk, to all the way to kind of having implants and embedded systems. But most importantly, you need more bits, more spectrum, more reliability, which in turn means you need above 6G and even above millimeter wave for enabling that. And this is primarily the focus of today's talk. So basically these two, the leftmost side of this figure. And if you look at the application services, let's say, the classical services, if you look at them into a 3-dimensional coordinate system that has latency, reliability, and rate, you can see that URLLC, which needs very low latency, very high reliability, it doesn't care much about rate. So the rates are really below megabit per second, or even, I mean, you could be 1 gigabit per second, but that's even a stretch. Usually it's very short packets, very small. And if you look at eMBB, another classical service, you don't care about reliability that much. You need low latency, maybe not as low as URLLC. And then you can now start thinking of other combinations of other applications. For example, mobile, broadband, reliable low latency communication, where you need low latency, maybe not as low, where you need low latency, you need high rate, and you need high reliability, but not as high as URLLC. You still need though high reliability. It's not like eMBB. So XR will fall somewhere around this MBRLLC, and we're going to talk about it later on. So it will be a combination of high latency, perhaps not ultra high, but low latency and high reliability, not ultra high, but still high reliability, and of course high rates, very high data rates. And so terahertz, because of the availability of the spectrum and because of the fact that you have high bandwidths, can potentially bring you very close to the high rates. It can bring you very, very close to this high rates region, and potentially, of course, reducing significantly the latency over the transmission, over the radio propagation link or the radio link. However, terahertz may have issues with reliability, and that's what we're gonna focus on. So a quick view again on terahertz. So terahertz will allow you not only to do communication, but also sensing. So terahertz, when I say terahertz, I really mean the sub-terahertz band, which is 100 to 300 gigahertz, as well as the actual terahertz bands, which is above 300, say 300 to 1 terahertz, 300 gigahertz to 1 terahertz. So we recently, posited that there are 7 features of terahertz bands worthy of exploitation. One being the quasi-opticality of the band that allows you to leverage better processing and communication aspects. You have to define terahertz tailored architectures using large surfaces. There is a lot of synergy with lower frequency bands. There's importance in joint sensing and communication, and that's a topic that's important for XR as well. I'm not gonna touch too much about it today. You have physical layer aspect, and we're gonna look a little bit at that today. So basically the reliability aspect and how that affects terahertz systems, particularly for XR. And there's spectrum access challenges and challenges in real-time network optimization. And of course, 4 potential use cases, one, the bigger one being extended reality, which we're gonna delve into today. So what are the XR challenges over wireless? So I touched upon them a little bit, but let's go into more depths at the system level, there are a lot of questions related to split computing. What do I do at the edge? What do I do at the cloud? You need a predictive analytics, and that's to predict behavior, motion, tracking, and so on. We've done that a lot in previous works. I'll mention it towards the end of the talk. Resource management is a big problem, and there's a coupling between uplink and downlink, between tracking and basically content delivery. There's a lot of challenges on the backhaul and compression, and those are aspects that are very traditional in some sense. But this is where I'm going to focus today, which is performance. So you need ultra high bandwidths and extremely high rates. And we all know sub-terahertz/terahertz will give me that. And you need near zero latency and jitter. However, we also need reliability with high rate. And this is the key challenge. And this is where I'm going to try to focus my discussion today. There's also issues of quality of physical experience. So how do we map raw quality of service like latency and throughput into a more subjective quality of experience like quality of visual effects or breaks in presence? And finally, there are a lot of energy efficiency challenges, and those are a little bit beyond today's talk, but they are very important in XR. So the focus today will be on reliability with high rates. So VR, let's take VR as an example, but again, the theoretical analysis can also extend to any type of XR actually. So on terahertz for XR and VR in particular, the advantage is the large available bandwidths and the ability to mitigate interference at least to some point. The disadvantage is the susceptibility to blockage, which we saw in millimeter wave, and it becomes worse at, again, sub-terahertz/terahertz bands. The molecular absorption, which limits the range of transmission, that is both good and bad. It is good because VR is really a confined space type of application. So we don't really need beyond that limited range. So having high bandwidth in a limited range is good. But the bad is also that you cannot cover larger areas. So if you have like bigger, larger VR applications, that's a problem. And that's something to overcome. And it's inherently unreliable because of these phenomena, because of the blockage, because of the molecular absorption. So the fundamental question, and that's what I'm going to answer today, is can terahertz frequency bands provide highly reliable, high rate, low latency communication? So it's really highly reliable, and that's a key word here, high rate, low latency communication. So let's call it HRLLC. It's not URLLC. There has been no prior works that study this problem. So this is not short packet 5G or your run of the mill 3GPP type of papers where we're gonna guarantee 99.999% block error rate for an uplink a traditional IoT application. That's not what we're doing. What we're doing is we're saying if you have very high rate and very high rates, meaning sub-terahertz bands close to hundreds of gigabits per second, and you need to maintain high reliability, maybe not to the extent of 5 nines, but even 3 or 4 nines. But now you don't have short packets. You have a very massive bandwidth intensive application that is extended reality or virtual reality particularly. What happens then? And is terahertz possible? Is it possible to do it at terahertz frequencies? So let's start with the system model. So let's consider a downlink of a cellular network where you have indoor terahertz base stations serving VR users. And we assume there's a Matern hardcore process for the spatial distribution, which is kind of particularly relevant here because we assume dense deployment. So you have a ceiling that's full of base stations that operate at terahertz frequencies. And we have an intensity eta for this Poisson process, for this point process, sorry. So we will assume that there's an edge computing server at the small base station, meaning that the computing is done at the edge at the base station, which allows generating the VR images and processing them. So first, let's find the model of the interference. So we assume there is interference because you have a dense deployment. So even if you have very small pencil-like beams, you will still have non-negligible interference because of the density of the network. So we take an arbitrary user on the ground at the distance R0 from the serving base station, and we try to find the interference surrounding this user within a radius of omega, which we're gonna call the region of non-negligible interference, which means outside this region, there's not gonna be any interference. It's just within this radius omega where you have interference. So again, we consider interference because we're a highly dense environment, and the beam realignment problem of pencil beam forming architectures may still be problematic. So you might eventually end up with still having interference among your base stations. So the interference model, we can find it in closed form. First, we can find the PDF, and it's essentially normal distribution. So this is not the major result, but this is a step towards our reliability study. So in this, you can see the region of non-negligible interference omega. Epsilon is just this parameter of the post-Sumatran process. So we have the mean of the interference and the variance of the interference here, sigma square. You can see the variance here and the mean. They only depend on eta, the intensity of the process, the point process, omega, the region of non-negligible interference, and again, epsilon, which is just a parameter of the matter and hardcore process. So in addition to interference, there's blockage. So we consider two types of blockages. One, which is the self-blockage, which is when a VR user blocks his own body blocks his base station or his transmission. So within an angle omega, we can see that could be a self-blockage between the user and himself. And dynamic blockages from other users that are arriving with a certain rate and that are going around the user and blocking his connectivity to the base station. So the probability of self-blockage is easy. We can find it as omega divided by 2 pi. It's kind of a uniform distribution here. And this is the angle with the blocked small base station. Then the probability of dynamic blockage is given by the probability of a dynamic blockage, knowing basically the radius and Q here, which is the number of blocked SBSs. So this is a dynamic blockage event. This is the number of blocked small base stations. And this will be a function of kappa and nu, which are essentially the arrival rate of blockers, the departure rate of blockers. So we assume that you have like a queue of arrivals. So you have arrival rates kappa and the departure rate nu. Then we can find the probability of simultaneous blockage of all line of sight links, meaning this user can no longer communicate, which is essentially a product of the total number of blocked SBSs. And this can be found in closed form. It's not very complicated. So this is the probability that a small base station is not self-blocked. And that's essentially a function, again, of the height of the users, the velocity of the dynamic blockers, and the density. So HB, HR, HT are the heights of the users of the blocker and the base station. So this is just a dynamic, a geometric, let's say, dynamic blockage model. So for a line of sight link, so later on, we're going to also use this blockage to find the probability of line of sight. But first, if you have line of sight, we use this Terahertz channel model. Again, it's not the best channel model, but since our focus is not on channel modeling, but more on performance analysis, whatever channel model you can give me later, I can plug it in and redo the analysis. But this channel model has been adopted in a bunch of prior art, so it seems a reasonable approximation. The key point here is this transmittance of the medium, which is very terahertz specific. You have the speed of light and the frequency and distance, and that's typical. But as I mentioned, the key here is this transmittance of the medium, which is function of an absorption coefficient of the terahertz medium. This is where molecular absorption starts to appear. And this is very unique for terahertz, as we will see here. So the transmission rate, which is the log 1 plus SINR, you can see here in the SINR, you have P0 and the constant A0, which are not significant here, but you have the radius and you have this transmittance, this K of F that I showed here, this absorption coefficient, which is inside the transmittance appearing. And this appears, which is essentially the main feature of a terahertz channel, and also the noise. The noise at the terahertz channel will be given by this equation, which is function of temperature, Boltzmann constant, but also function again of this K of F, which is essentially the absorption coefficient. So you can see there's an absorption coefficient that appears, which is very unique to terahertz, along with your regular, pass loss and so on. So you can see that there is a significant gap in terahertz or sub-terahertz. There will be a significant gap between line of sight and non-line of sight. So we assume that the non-line of sight link has a 0 data rate. So the probability of line of sight is our next goal. So the capacity will be probability of line of sight multiplied by CL plus probability of non-line of sight multiplied by Cn. We assume this to be 0. So we only need the first term. So we need to find the probability of line of sight, which is essentially found in this proposition. The probability of non-line of sight using the blockages and everything we derived before can be given in closed form. So this is the first, sorry, I quickly clicked all the slides. The probability of line of sight is given in closed form here. It is basically function of these departure and arrival rates of your, the departure rates of your blockers and the region of non-negligible interference. And this shows the susceptibility of terahertz links to network parameters as an exponential. So there is a very large susceptibility to blockage. The key factors that affect this is the density of the blockers and the region of blockage, or the sector of the disk of self-blockage in some sense. So these kind of affect significantly your line of sight probability. So now back to the real deal, the reliability analysis. So now we know we have a terahertz network. We have the physical layer model, which is pretty standard, I would say, and then we can derive the probability of line of sight. Now, knowing that, the question is, can I study reliability / latency, because they kind of come hand in hand. So to analyze reliability, we must first define it. So we define it as a function of the end-to-end delay. So we assume reliability to be the probability that the end-to-end delay is below threshold. What this means is looking at, again, a mobile edge computing server. Here you have a user requesting basically VR images from the server, which is base station. Those requests in a Q1. Then it will process these requests to create the VR images and content, then transmit those to the transceiver, which will queue those images and then transmit them over the terahertz channel here. So end-to-end, the delay is basically end-to-end from the generation all the way back to the user. We assume the uplink is negligible, so we don't take into account this uplink request. We just look at this sequence of 2 queues. So Q1 is the processing delay, the queuing and processing delay queue, which will be an MM1 model, and Q2 is the transmission delay, essentially. So the queuing and transmission delay, which will be an MG1 network. So in Q2, you are queuing the content to be transmitted, and you have the transmission delay over the channel here, and you have the queuing delay at transceiver. So it's an MG1 model. So how do we define reliability? Let's go back to 3GPP. So this is copied and pasted from the 3GPP. So they say that reliability should be defined as the capability of transmitting a given amount of traffic within a predetermined time duration with high success probability. Many people translate this into block error rates, which is of course perfectly fine, but we go a step further. We say that a predetermined time duration, and we have a low latency here, so we want to go a step further and say this definition is necessary but not sufficient, because when we want something like VR and going into this high rate, high reliable low latency communication, we need to satisfy a quality of physical experience, which requires both perceptual and haptic requirements to be satisfied. So they have to be satisfied instantaneously, and those translate essentially into the rate / delay. So they will have to be guaranteed instantaneously, because otherwise, I mean, you lose your sense of immersion, your sense of being in the virtual world in some sense. So how do you analyze reliability? There are many metrics to analyze it. Let's say we're going to look at it as the end-to-end delay. How do we look at it? So some people look at averaging. Averaging is good, but that's not necessarily always the best case. There are ways to look at it through percentiles, which is also good, but not sufficient. There's also some risk measures like this value at risk, the VAR region, which tells you basically what is the probability of achieving, let's say, a target with a certain risk measure. But unfortunately, the VAR itself by itself is not a consistent or coherent risk measure, so we need a little bit more than that. So we don't want to look only at averages, which can portray a positive viewpoint. We want to look primarily at the tail. And the tail distribution sometimes is studied using something called ruin theory, which is basically the maximum severity of reaching the tail. And we're going to explain what we're going to use there is particularly. We're particularly focused at reliability in face of extreme events, meaning a sudden traffic surge, a sudden blockage, a sudden fade in the channel, and so on. So a sudden change of your environment that kind of jeopardizes your VR experience. So we're going to look at tails, but not just that. We're going to try to guarantee the high reliability at the tail, to maintain no instantaneous disruption, and to basically assess the tail. Looking at only the quantile value, as I said before, does not give you a probabilistic viewpoint of the reliability. So instead, we might want to look at multiple quantiles, or particularly what we want to look at is the distribution of the tail. So for example, here you have two distributions with the same quantile, but they have very different tails. So looking only at the tail is not sufficient. What we want to look at is actually the distribution of the tail itself. And that's a step further than any other reliability analysis that was done before. So we're looking at the distribution of the tail for all probability values. This is why we rely on generalized extreme value, which is a statistical tool. And this allows us to view the distribution of the reliability for different extreme events for their different likelihoods as well. And to provide guarantees, we're going to use this metric called tail value at risk, which uses the GEV to basically tell you, with a certain confidence level, I'm sure to achieve this reliability. With a certain confidence level, this is what I can achieve. So it will introduce this confidence level in the percentile to assess the performance during worst case, of course, extreme events. So with that said, we need to find basically the distribution of the tail. We need to first find the first order moments of the end-to-end delay. That's the first step, and that's an important step. So the first main theoretical result is we characterize in closed form the mean of the end-to-end delay. This is the average. This is an important metric by itself, but it's going to be a means to an end to find the tail. So in this case, you can see it looks complicated, but it's not that complicated. So it's function of the service rate at Q1, which is how fast are you processing images. It's the arrival rate, how many tasks are arriving from the users. It's also the utilization of Q2, so how much content is coming into Q2 and how fast is your transmission rate, your data rate. It's function of the transmission delay, of course, that's the main parameter, and this appears here, the expectation of the transmission delay. And it's, of course, clearly function of the transmittance of the medium appearing here in your denominator. So the average end-to-end delay turns out to be equally influenced by the mean of the waiting time for processing, the utilization of Q2, which means how high is your data rate in some sense, and the mean of the transmission delay. The waiting time, though, of Q1, keep in mind, it's only influenced by the number of VR requests and the processing speed. So it's not a wireless controlled environment. So the average transmission delay also depends on the average blockage rate and the average terahertz data rate. These appear here, and they also appear of this this function. You can see here the eta of the Matter and hardcore process. You can see the omega that I showed before, and this calligraphic n in some sense. So now we need the second mode. So first, again, keep in mind this alone is a significant result. This has not been derived before, and it's not an easy proof. It's not a matter of applying little theorem or something like this. There's quite involved derivation, and this already shows you what is the average end-to-end delay you achieve for VR over wireless or over terahertz particularly. So the second moment is also needed for us to find the tail. So again, a lemma here. And the second moment is function of somewhat the same parameters as the first moment. And having the first and second moment, we can derive higher order statistics, and this allows us to characterize the data distribution using the known Fisher-Tippett Nedenko theorem. And this is the main result, essentially. We have the tail distribution. It follows a GEV. Again, looks complex, but it's not. These are the shape and location parameters. What's important is the parameters we're dependent on, and this is very tractable. It depends on the number of samples you collect, and it depends, you can see on alpha, the transmission delay. These are the higher order statistics. Depends on the utilization of the Q2, depends on the transmittance of the medium, depends on the blockage. So you can see now we have the worst case distribution over all possible outcomes of randomness, rather than just an average value or just a tail distribution. So the distribution of the tail is centered around the mean, and that's kind of expected, while the variance is influenced by the three moments of the data rate and it's of the terahertz data rate and its susceptibility to the environment. Now you can see how, yes, we can achieve high rates. We know that, but it's starting to appear that those data rates are influenced by other parameters like the blockage, like the waiting time. So reliability may not be always guaranteed. So obtaining the tail and the distribution, we can now define our level of risk, which is the TVAR. So we use the TVAR, which is a coherence risk measure, better than the VAR as well. And it not only measures risk, but gives us this confidence level. So we can find the TVAR. This is not a very difficult mathematical. Once you find the theorem 2, this one is not that hard. So we can find the TVAR. Alpha C is the confidence level, which means 90% of the time I can guarantee this reliability, or 99% of the time I can guarantee this reliability level. So this is function of basically your transmission time and your different parameters. So and this allows us with the TVAR now, I can know. So I'm not claiming anything. I'm asking the question, can terahertz be reliable? With the TVAR and coupled with the GEV of the tail distribution, I can know if we can have a seamless experience or not. So with a certain confidence level. So we also gonna, before I show you the simulation results where we can see a lot of insights, We also can study a very special case. It's interesting to understand, actually, where the line of sight is 1. Let's assume blockage is not a problem. I can guarantee line of sight. What happens? In this case, the calculations becomes easier. So we have a continuous line of sight. In this case, you don't need the tail because you can actually find the distribution. So we can find the CDF and PDF. So for the NM1Q, the delay PDF can be found from classical textbooks. It's not very difficult to do. So this is kind of a known. It's function of the service rate, which depends on the channel, and the arrival rate. Sorry, service rate, this depends on the processing power, not on the channel. Mu2 depends on the channel. And at Q2, which is an MG1, we can find the CDF of the waiting time, which is a convolution of this psi Q2 with psi of t. So this is the CDF of the queuing time, which is known from the queuing literature. And this is the PDF of the transmission time, which we derive. So we derive the PDF of the transmission time. You can see with guaranteed line of sight, it's a special case, but it's very, very tractable, actually. So you don't need to do a lot of elaborate mathematical analysis. And we can find this function of the packet size, the transmission delay. So I'm not going through all the parameters because they're all the same. The difference is that here I'm finding the exact PDF, so I don't need to rely on other statistics. In the previous case, you cannot find the exact PDF, so you need to rely on statistical analysis. And we can find the CDF of the end-to-end delay in closed form here. So it's not that hard with the convolution even. It's not that difficult. So consequently, the reliability with respect to a certain threshold can be defined as the probability that your end-to-end delay is less than double. And I mean, this is a tractable characterization. We have 2 views now, right? The first view is the general case, where I can derive the distribution of the tail and the tail value at risk, which tells me, well, if I have this configuration of your terahertz network, these parameters of your VR network, this is exactly how reliable your delay will be. This is how long or how much your end-to-end delay will be below a threshold instantaneously. If you have guaranteed line of sight, the mathematics becomes easier and you can find the exact reliability directly from the CD. So again, you can see it will be dependent significantly on the transmission delay, which will be dominant. And it will depend on the molecular absorption as well, which will impact reliability. In this case, I don't say it's dependent on the blockage because I'm assuming no blockage guaranteed line of sight. So let's see the simulation results. Again, a quick summary. So 2 views. The question was, can terahertz deliver reliable VR? We know, and everybody agrees, that terahertz can deliver high data rates, high bandwidth, as much you have a lot of bandwidth, and you can use as much of it as you wish. The question is, can that bandwidth maintain or sustain an instantaneously high rate, which kind of equivalently means low latency, for applications like XR? The answer will appear in the numerical results. What we did theoretically is we quantify it, we give you a tool to actually inspect and scrutinize that tail for different parameters and understand, in this situation, you are reliable, in this situation, maybe I'm not reliable. So you can study all those conditions. We studied it for the general case with blockages and for the case of guaranteed line of sight. So first, a quick corroboration of our theoretical results. There, they match the simulation. So you can see that the theoretical results match the simulation. This is kind of expected. And that's just a corroboration of the theory. So there is a small gap in this figure, which comes from Jensen's inequality. And here we assume this normal distribution. So there's also a small gap, but that's not a big problem. So this is the most interesting result. So here we look at the average end-to-end delay, the instantaneous end-to-end delay, and the tail end-to-end delay. So if you're doing your analysis based only on averaging, then you would think that your terahertz network is very good for VR. So your average end-to-end delay is below 20 milliseconds. That's kind of saying that you're within what is expected from some immersive applications, and this looks fine. Then things start to look a little bit less rosy when you look at the instantaneous end-to-end delay. You can see that there's at least one spike, which goes to 80 milliseconds. That might not be very important if you're doing a file download, right? But in a VR environment, assuming you're fighting Darth Vader, and all of a sudden you know Darth Vader is just a door in your room, that ruins the entire experience, right? Or you try to raise a sword inside your VR experience, and that doesn't happen. So that's very kind of concerning. Now, when you look at the tail end-to-end delay, you can see that the average tail is around 50 milliseconds, and that's a very negative view of the achievable performance. So you can see averaging is not the full picture. instantaneous gives you some insight, but the tail gives you really a clear view that there is a problem of reliability. Now, I will talk later about possible solutions and so on, but the reliability may not be as much as we would like it, especially if we move towards terahertz. And again, every time I say terahertz, I mean sub-terahertz, which could be 100 to 300 gigahertz or above that. So our analytics can work for either environment. Here I'm showing for 1 terahertz. In the paper, we show for 200 gigahertz as well, and there's very similar results. So any extreme event will lead to a minimum end-to-end delay of 30. This is based on the tail here, and that's not great. So now looking at the TVAR, this is the confidence level. So I want to guarantee a certain millisecond, or here I say, let's say 30 millisecond or something of the sort. So I want to guarantee a certain delay with a high confidence level. You can see with high confidence level, you cannot really guarantee much. But you can guarantee 30 milliseconds with 80%. That's kind of fairly easy to do, but it's very difficult to keep a low end-to-end delay with the risk percentile above 90%. And again, I said before, I'm not aiming for HRLLC. This is probably not necessary for XR, but something around 90% of confidence level might be useful. And that's not clearly achievable, at least in this case. You can see that bandwidth, increasing the bandwidth improves things, but you're still limited. You're still, I mean, you don't go very low when you look at the tail value at risk. So it does improve though your performance. So now looking at the delay versus bandwidth and the reliability versus bandwidth. So in these figures, you can see the two cases, the guaranteed line of sight case and the general case. First, for the general case here, looking at the two delays, Q1, which is the processing delay, Q2, which is the transmission delay. Q1 is not affected by the bandwidth because this is just a computing delay. Q2 clearly goes down, but it's not, I mean, it goes down, but not as steeply as you wish at the end. So it saturates somewhat. So it's still a significant delay. I mean, you would think for immersive experiences, this is still a significant delay. Now, looking at the guaranteed line of sight case, which is the light blue and green, you can see it's much, much better. So with a guaranteed line of sight, high bandwidth, probably you can achieve the level of delay and reliability that you want for VR. But here, guaranteed line of sight, and that's a big if. So looking at the reliability now, we can see a similar view. If you have 10 millisecond target without line of sight, you can barely achieve maybe 70% reliability with very high bandwidth. If you have the same case with guaranteed line of sight, this goes significantly above 80%. 20 millisecond with guaranteed line of sight, you're very close to the 5 nines actually. So it seems like line of sight is key to guaranteeing reliability. So again, this just repeats what I just said. In presence of blockage, the reliability is limited to 68 to 96% for 10 millisecond, 20 millisecond, even if you have significant bandwidth. In guaranteed line of sight, a bandwidth of 15 gigahertz achieves the 5.9. But again, this is a big if you need a guaranteed line of sight. Now, looking at the end-to-end delay versus the molecular absorption, you can see that with guaranteed line of sight, you have very low delay. With blockages, it's very, not just higher, it's also not very smooth. So you can have a lot of changes in the achievable delay because molecular absorption changes a lot. It depends on the environment. I've seen a lot of works now claiming, okay, there is a certain very specific region of molecular absorption where propagation is amazing. These have been partially validated, but they're not generalizable claims. So we can say, yeah, maybe in this very specific environment with some very specific use cases, you might find this sweet spot that's kind of a rosy area, but that we cannot generalize those. So here we can show for all the ranges of possible molecular absorption. And you can see the same with the reliability. Higher coefficients lead to lower reliability. Again, the guaranteed line of sight, these lighter figures are always better than the general case. And as a numerical example, for the threshold of 10 milliseconds, the availability of line of sight gives you a 13% improvement in reliability. And that's a lot. When we talk reliability, it's not like just a few bits per second extra. It's a significant improvement. And finally, one looking at the reliability versus the region of non-negligible interference for the guaranteed line of sight case. So here we can see that the sensitivity to the distance, so how far the user is and how slow. So compare the blue curve with the red curve. The further away you are, the further away, the closer you are, then the region of non-negligible interference is larger. So you have a larger region where you might have interference because you're kind of closer to the different base stations. But essentially, this is saying that for larger distances, you are more sensitive. Your performance, your reliability is more sensitive to basically your parameters, your delta and your d0. So again, this is the reliability versus the region of non-negligible interference. You can see that for smaller distances, you can achieve better reliability. For larger regions of non-negligible interference. For larger distances, like the red curve here, it's worse. But keep in mind, this figure is guaranteed line of sight. So a summary of the answer, and then I'm gonna do a broad overview of our other works, which are also of high bandwidth in general, and then we'll conclude. So the question was, can terahertz provide high rate, reliable, low latency communication? Well, the answer is, well, it is necessary to have a high bandwidth and operate at regions of low molecular absorption. Again, these regions, some people claim there are many of them in the terahertz spectrum. Others say no. In general, what I would say is they're environment dependent. We don't know exactly, but you could have a positive region. So this is necessary. But extremely events resulting from the unavailability of line of sight are still a problem, even if you have these two very favorable scenarios where I have this high bandwidth, a huge bandwidth of terahertz. I have this very favorable molecular absorption, low molecular absorption. To improve a line of sight, you can use RISs, and we were the first to propose that at terahertz. I'm going to discuss that in a moment in a single slide, where we said, okay, based on the results of this paper, we can use RIS to guarantee line of sight. And I'm seeing a little bit more in that regard now. Using RIS, I mean for terahertz, not the general RIS, which has been around for years now. And it is fundamental for you to look at the tail and the distribution of the tail to understand what you can do in extreme events. And this is, of course, important for XR applications. If you're looking at applications that are more tolerant, then probably you don't need a tail. So during a typical, again, VR session, the delay can range from 30 to 90 milliseconds, which is an unreliable experience, even if the average is 20. And after guaranteeing line of sight, you still have to overcome the short communication range of the molecular absorption, possible interference from density. So there are a lot of challenges, but this gives you an answer. It says that XR over terahertz is promising, but we need some favorable conditions. One is low molecular absorption and high bandwidth. High bandwidth is probably easy to have at terahertz. Second is guaranteeing line of sight, which is challenging. But even with line of sight, you still need to maintain your low molecular absorption. And even if the molecular absorption is low, the distances might be short, and you still need to manage that. So as I mentioned, there could be a solution, and this is using RISs. So RISs allow you to have a higher probability of line of sight. They allow you to control the environment propagation. And I'm sure everybody knows what RIS is. They have passive elements and they do not require power sources. So how do we associate those meta surfaces in a room to RIS to VR users? And this was the ICC paper of last year, where we proposed the use of RIS inside to basically guarantee your line of sight and allow your terahertz to operate properly. So here we looked primarily at cell association to guarantee line of sight. And we used risk-based learning. We can show that the proposed approach, which is a risk-based policy controller, is as good as an optimal solution here in terms of the queue length. And in terms of the sum rate, it's not too far. For example, U is the number of users. So if you compare the two squares here, the red square for U equal to 7, which is a dashed line here, with the optimal controller, which is the dashed line here, you can see that we're not too far. The sum rate, we're very, very good in terms of how we manage the queue. So you can see that helps things. And again, this is just a step towards improving VR experience over terahertz. Now, what are other interesting problems in this space? So this is a little bit of a change. So we looked also at the augmented reality use case. So in the augmented reality use case, I want a real-time interactive experience with the virtual components, which means I need to guarantee fresh information at the server. So the information it's not just about delay, it's about how new or old is this information, which is typically quantified using peak age of information, which is a metric that many people know now, which was proposed by Roy Yates, and it's a very popular now. So we looked at an AR case where you have uplink AR requests that can come through either first come, first serve or last come, first serve queues, and they're requesting AR content. And we looked at, again, ruins, basically the risk of being in a tail, if you want, the risk of data freshness falling below a certain tail. Turns out that mathematically, ruins, which is studied in the economics literature, is very, very much similar to the dynamics of MG1 queues. And we were able to make that kind of connection of the two and to find how you maximize, what is the maximum severity of peak age of information. So what is the worst case you can achieve if your information is not fresh? And we can show some results here. These are interesting. It shows you the average peak of peak AOI versus bandwidth, and then the probability of achieving a certain freshness, if you wish, versus bandwidth. What's important is increasing the bandwidth improves the peak AOI, but it affects negatively the worst case performance. The bandwidth may affect your worst case performance because there's a higher likelihood of having terahertz related extreme events. You have a more pronounced molecular absorption effect. And that's very interesting to see. And of course, we can see that the first come, first serve is better for the average, while for a risk-based approach, last come, first serve is better. So with that said, I mean, this is a GlobeCom paper from last year. With that said, just a broad overview on our research areas, others, and then we can conclude. So we've been doing a lot of work on AR. I already talked about this with wireless, but also other aspects of reliable low latency of a wireless system. We've been doing quite a lot on this collaborative autonomy use case from learning. Yeah, I had a disruption in my.
Yes, we lost you. So if, yeah, now we can. Oh,
42 or 43. Do you recall which slide?
Yeah. This one was covered, but whenever you said that, you will start saying about work at. So GlobeCom was mentioned. Okay, so then you stopped at this slide.
Yes, so it was at this slide. So I was saying, so some of our research. So we've been looking quite a bit at the ability of having low latency communication while also having machine learning tools that allow you to do that low latency communication. So basically this convergence of learning and communication, including generative adversarial networks, federated learning, and other tools. We've been looking a lot at terahertz. I mentioned early on this fellowship of communication and sensing. This is something that's ongoing, and also the look at RISs and applications that have human in the loop in addition to XR. We looked quite a bit at connected drones and connected autonomy, from learning to control, connectivity, and security. I have a group of students looking more on the learning side, basically how to improve machine learning itself, how to make more reliable learning and more the ability of generalizing from small data, basically using federated learning and other tools. We have a major project looking at age of information from different angles, including use cases like AR, including fundamental analysis, including mean field game theory analysis. And we do quite a bit of game theory. That's kind of the center of our work in use cases. We also have some other applications, other projects related to power systems, more on the optimization game theory side. And we're looking at some smart city applications related to optimization as capsule networks and blockchains. So in conclusion, XR is a very exciting area. It brings forth many challenges for 6G, really, not just 5G. 5G can do XR, and they will do a lot of interesting and amazing things, but they will fall short as soon as you want this very, very immersive experience. And terahertz, and again, when I say terahertz, that includes sub-terahertz all the way up. It will provide high bandwidth. It's really good, but there's reliability questions there. And there's a lot of work now looking at the physical layer. I was trying to kind of convey here that we should look at also other angles, meaning more network system level analysis. And there's a lot of fields coming together here: risk, learning, wireless, and XR. And I mean, this paper is a TWC paper, which is soon to be, I mean, we revised it already, and it's on the review. And finally, thank you, and I'm happy to answer questions with you early on. So this was not very reliable, I guess.
Thank you very much. Very interesting. Yeah, yes, in the last 2 minutes, maybe it was not very clear, but yeah, amazing the presentation. So we have some questions from audience. So Mohsen Gizani asks, okay, knowing that Terahertz can support new network speeds, but what are the disadvantages of Terahertz and the challenges to achieve communication at Terahertz?
Yeah, I think that's a great question. Let me go back to the slide, which was the beginning, and that will help. Will help us kind of cover everything. So, so this is a recent paper which we have on archive already.
Walid, we don't hear you properly. Hi.
Yeah. I was switching to this slide, so I was answering and saying that in this recent work, which is now on archive, we actually looked at the comprehensive view of the. Can you hear me now?
We hear you, but not very clear. I will be turning off my video. Maybe that will save some bandwidth.
Yeah, I will do this. Is it better now?
Maybe, yes.
Yeah, okay, so I will try.
Yes.
Please interrupt me if you feel that there's a connection issue. So
go ahead.
What I was saying is we identified 7 major challenges of Terahertz that you can see them in detail in this recent paper. So the first one is the nature of the band, the quasi-opticality of the band, which means that there are hardware challenges, how to implement even FDM and FDMA, how to implement those, but also there's these issues of molecular absorption that I discussed in this talk, the high susceptibility to blockage, the shorter range. Again, there has been some work portraying a very positive view of that, saying, oh yeah, there is molecular absorption, but there are sweet spot regions within like a certain band where you can really do good. That could be the case, but that's very environment specific. So you still need to overcome those challenges. And to do that, you need Terahertz tailored architecture. And that's the second challenge that you can see here, which is essentially, what is the network architecture that allows Terahertz to blossom? We can initially start indoor, and indoor is okay, but then if we want to go outdoor, what can help it to blossom? So this brings in cell-free massive MIMO and the possibility of using holographic surfaces, which helps a lot in that. The third key challenge is basically leveraging the synergies between the frequency bands. So Terahertz alone will probably not work separately. You need synergies and support from millimeter wave and sub-6 gigahertz. So how do you manage that? Fourth, which is a challenge and opportunity. So Terahertz is particularly good at sensing the environment. So people call it imaging, and there's a lot of terminology there. I prefer the term sensing, which is essentially object tracking and object detection and tracking, essentially, and localization in some sense. And this allows you to help in communication as well. So can you do this joint sensing and communication? 5, there are a lot of physical layer challenges, from initial access to developing beamforming techniques that work well. There's a lot of spectrum access challenges. How do we use NOMA? Do we use OEM? What type of multiple access can we use? There's real-time network optimization challenges, and this I touched a little bit upon. How can you make sure, okay, I know there's reliability challenges. How can I make sure to get that the network manages the resources in terms of beams and time and so on to ensure that you're sustaining that? So I think these are like 7 key challenges of Terahertz bands. And I hope I'm still connected to take the next question.
Yes. Thank you very much. Yes, we hear you now properly. The second question by Haytham Dahrouj is he asked that beside RIS, can the trade-off between high rate, reliability, and low latency be achieved not only on terahertz but on a hybrid system, terahertz and other RF-based communication? So, what do you think about this hybrid systems?
Absolutely. This is, I mean, I'm actually pointing to it. So this is the number 3 here, which is the synergy with the frequency band, and that's essentially being able to leverage all of them: sub-6 gigahertz, millimeter wave. There are, of course, hardware and more like implementation challenges there, but from a network perspective, you can kind of balance things across to maintain low latency. You know, use terahertz when it's good, do some information shower when terahertz is available, and try to kind of hand over to others. But again, there's a lot of control plane challenges there as well. But I think I'm already pointing to it, and I agree completely that that's a great way to look at that.
A question by Sami Khairi. Okay, he says that what conditions we need to have or to assume for the tail distribution to follow a generalized extreme value distribution?
Actually, there are no major assumptions there. You can it's a little bit like like in machine learning, like the Dirichlet process, which is in that case where you don't know a prior, you can assume it to be Dirichlet distributed. In this case, when you have a tail distribution and you don't know what it is, you can assume it to be a GEV. If you are able to find the moments, you can find an expression for that. So there are no stringent assumptions made for that.
Okay, good. A question by Zubair Fadlullah is, will attaining the synergy between terahertz and the lower frequency bands actually help? Okay, because he says that because the lower frequency bands are assumed not to be able to support XR services.
Right. I mean, they can help in different ways, right? So first, when I say lower frequency, there's also millimeter wave, which is a little bit longer range, and I mean millimeter wave meaning below the 100 gigahertz, which is already very useful, not just sub-6 gigahertz, but sub-6 gigahertz provides you with some reliability, right? So it can help, for example, in supporting, let's say, control plane transmission. It can help support handover. Some of those decisions that can be very susceptible to blockage, let's say, on terahertz, but that can be much more reliable on sub-6 gigahertz. So yes, there is a tension between bandwidth needs and basically reliable connectivity, and having the two helps you basically balance these two angles.
Very good. And one last question is this still the consideration of the tail to check for the quality? Does it represent some kind of worst case scenario, or do you think that?
It does represent a worst case scenario. It does represent a scenario where you would have extreme events that are happening, but keep in mind, these are worst case scenarios that are inherent from the channel. It's not that we're, it's not like the case where, you know, I want to study with 1 million users and then I take the worst case of 1 million users and see what happens. No, here I'm saying that this channel has worst case points, and these worst case points can happen and they will disrupt your channel. So yes, it is worst case, but it's an inherent worst case that's kind of part of the system itself.
Yes, seems very interesting. Okay, so let me check if we have, because we have on the question and answered on the chat. Yeah, we are done with questions, and we would like to thank you again for the nice presentation. I should say that the recording will be available at the CSIM website for anyone who is interested to download it. And if they have further questions, you can contact Professor Saad by email.
Thank you so much.
So yes, thank you again. Thank you for all the attendees, and looking forward seeing you and meeting you all in future CSIM webinars. Thank you very much.